Okay, so we have been talking about exponential functions. We are moving into exponential growth and decay. I really like this section because I think it's one of the most practical things that we talk about. This is something that you are going to see in real life. You will use this when you get older, and so it's a good thing for us to talk about. So, vocabulary. Exponential growth. This is going to feel pretty obvious, I think. But exponential growth is when a quantity increases, or when a quantity increases and I'm going to say over time. So one of the things that we're talking about when we talk about exponential growth and decay is we're talking about things that happen over a certain time period. And so most of the time that time period is going to be in terms of years, but it's over a certain amount of time. Something else I want to mention is that this also assumes that we are dealing with an exponential function, right? So it's when a quantity increases exponentially over time. So not just a linear function in this case, it has to be an exponential function. And if you remember, the form for our exponential functions is y equals a times b to the x. This is going to stay the same. So a is where we start. B is what our change factor is. All of this is staying the same. So if we're dealing with exponential growth, it's the same thing as when a function increases. Our b value, our change factor, needs to be greater than 1. Okay? Then we have what we call an exponential growth function. So exponential growth is the term that we use to describe what's happening. The actual function is the equation that we use to figure it out. So exponential growth has this equation. Y equals a times 1 plus r raised to the t. Okay, so a couple things we need to break down in here. Y equals is the same thing. A is still our starting point. Okay, so if we're talking about money, it's our principal, it's our starting value. R is our growth rate. Okay, so R is going to be given to us most of the time in terms of a percent, but we always want it to be a decimal. Now we're going to be raising this to the t power. The reason being that we are talking about time now, more specifically. So being raised to the t power reminds us that we're dealing with time. There's a couple parameters that I have here. A needs to be greater than 0, and R also needs to be greater than 0. And this makes sense when we think about it, because if I start with nothing, and is it going to increase when I multiply it by something? And the answer is no, right? If I multiply anything by 0, it's going to be 0. So if I start with nothing and I apply some interest rate to it, it's not going to automatically grow into something else. Also makes sense that our rate of change needs to be greater than 0, because if we are changing, we're going to change in a positive way. Okay, so let's just say, for example, in this case that our, let's do this over here actually. Let's say that our rate of change is 25%, and I'm going to say that my starting value is $100. Okay? If I'm using this equation, I would say, well, y is going to equal, starting with $100 times 1 plus 25% as a decimal is 0.25. And then I'm raising that to the t power. Okay, and I can simplify this. So simplified, this would be y equals 100 times 1.25 raised to the t. Okay, and that's what that's going to look like. Exponential decay is very similar, just the opposite. So it's when an exponential function, when a quantity decreases over time. When I have exponential growth, my b-value needs to be greater than 0. With exponential decay, our b-value needs to be between 0 and 1. In other words, it's going to be a fraction or a decimal. Either one, right? It's just going to be between 0 and 1. So our exponential decay function is also very similar to our exponential growth function with one small difference. It's still going to be y equals a. It's going to be times 1 minus r raised to the t. My parameters for this one then are that my a value still needs to be greater than 0. That's still true. This time though, my r value is going to be between 0 and 1. So it's going to be a fraction. Okay, let's use the same parameters from up here. We'll say that r equals 25% and a equals 100. So we would have y equals 100 times 1 plus, nope, not plus, it's again messed up, 1 minus 0.25 raised to the t. If I simplify it, I get y equals 100 times 0.75 raised to the t. Okay, that's exponential growth and decay. Like I said, it's very similar to what we were talking about with increasing and decreasing functions. The main difference in this is that we're just getting a little bit more specific about what we're talking about. Last one, this is probably one of my favorites just because this is like so practical. You're going to use this so much. Compound interest. So compound interest is interest earned on principal plus previous interest. So this is when we talk about like we earn interest on top of interest. It's interest earned on principal plus previous interest. So we have kind of a big, maybe a little bit confusing equation for this, but I'll go ahead and write it and then we'll talk about it. So we've got y equals principal, okay, that's what the capital P stands for. Still going to use 1 plus in this case, and then I have my r, my rate of change, over n raised to the n times t. So we're going to write what each of these components is. So principal is our p. That's what I'm starting with. R is our rate as a decimal. Then we have this new one now, n. N is the number of times compounded. Okay, and what I mean by that is how many times do we run this function every year is kind of the more specific way to say that. And then we have t is our time, and that's in years. So here's how compound interest works, right? So I put some money in the bank. It is earning interest. And let's say that it is earning interest monthly. So what is happening is that this amount is compounding monthly. So what that means then is the number of times that it compounds in a year is going to be 12. We'll do an example of this later, so it'll make some more sense. But that's what we mean when we're talking about that. Okay, let's do an example. So the inaugural attendance of an annual art festival is 80,000 people. The attendance Y increases by 6% each year. Write an exponential growth function that represents the attendance after T years. we will start there. So remember our formula for this is going to be y equals a times 1 plus r raised to the t, okay? And it's really honestly just plug values in and we're done. So I'll have y equals, my initial amount was the 80,000 people, and then I have times 1 plus, my rate is 6%. 6% as a decimal is 0.06 raised to the t power. I can simplify what's happening in the parentheses. So what that means is that my equation is 80,000 times 1.06 raised to the t power. There is my function. And that's it. Part B then says how many people will attend in the 5th year, round to the nearest whole number. So all that this means, the 5th year, remember t is our time in years. What this means is evaluate this when t equals 5. So here's what we're going to do. Y equals 80,000 times 1.06 raised to the 5th power. Here's a good thing to remind yourself of. We have PEMDAS, okay? And really the part that we are paying attention to is parentheses and exponents happen first, right? So that's why here I could add what's inside the parentheses first, because that's the first thing that I do is parentheses. After I'm done dealing with parentheses, then I move on to exponents. So as you are doing this, let's see if my calculator can do it this fancy. I don't think it can on here. Maybe I can. Cool. Scientific? That's what we want. Okay. So we can do our 1.06. Okay, and we are going to raise this to the 5th power. We're going to do that first. Okay, that equals 1.38338, whatever. Once I've done that, now I'm going to take this times 80,000. And order matters here because, and I will show you why in a minute. So we should have gotten around to the nearest whole number, 107,058. So it would be 107,058 people is our solution. If I had not done the exponent first, here's what people like to do. They like to do, let's clear this out, 80,000 times 1.06 and then raised to the 5th power. This is what happens when you do that, right? This is an outrageous number that makes no sense whatsoever. Okay, so this is why order really matters with what we're doing, because this answer is completely wrong. Completely wrong. So make sure you're really breaking it down step by step when you are punching this in your calculator. Okay. Identifying exponential growth and decay. So determine whether the table represents an exponential growth function, an exponential decay function, or neither. So first, when we're looking at these, we have to decide whether or not it's exponential, and then we can figure out if it's decay or growth. So here's what we're looking at. If I go from 270 to 90, I'm dividing by 3. 90 to 30, dividing by 3. 30 to 10, divide by 3. So when we're dealing with an exponential function, really what we care about is, are we multiplying by the same factor every time? But think about how multiplication and division are related. So let's just say I had like 2/3 divided by 3. If I'm dividing fractions, I have my keep, change, flip, right? Keep the first one, change the sign, flip the second one. So dividing by 3 is actually the same as multiplying by 1/3. So really what's happening here is I'm multiplying by 1/3 every single time. So yes, this is exponential, and I'm going to put exponential. My values are decreasing every time, so it's going to be exponential decay. And it's as simple as that. Maybe I'll write up here, so if you need this, 2/3 divided by 3 is the same thing as 2/3 times 1/3. Okay, if we look at the second one, we're going from 35 to 29. That's a -6. That's a -6. 23 to 17 is a -6. So this is neither, because I am not multiplying by the same factor every time. This is a linear function. So it's not even exponential. It's linear. Last one, if I go from 6 to 24, I'm going to multiply by 4. 24 to 96, I'm multiplying by 4. Multiply by 4 again. Yes, this is exponential. And these numbers are getting larger, so this is going to be exponential growth. Okay, great. Let's move on. Okay, so determine whether each function represents exponential growth or decay, and then identify the percent rate of change. Percent is important. All right, first, let's figure out if it's growth or decay. So I have y equals 4 times 1.09 to the t. Now, remember, I have these functions over here that tell me what happens in each case. Exponential growth happens when b is greater than 1. Exponential decay happens when b is between 0 and 1. So in this case, my b value is greater than 1. It's 1.09. This is growth. And I would probably write to the side here that b is greater than 1. That's how we know that it's growth. So then we want to know what is the percent rate of change. So if we're talking about a growth function, we would have y equals a times 1 plus r to the t. If we're dealing with decay, we have y equals a times 1 minus r to the t. So I want to know what the percent rate of change is. Well, the way that I get this 1.09 is I add these two things together. So what I can say is that 1 plus r needs to equal 1.09. Then I'm just going to solve for r. Subtract 1 from both sides. R equals 0.09. What it is asking me for is the percent rate of change. So my r value is 0.09, but the percent rate of change is 9% growth. It is increasing by 9% every time. So if we look at part B, I can notice that my b value in here is between 0 and 1. So that means that this is decay. I know that because 0 is less than b is less than 1. So go ahead and pause the video now and figure out what would the rate of change be for part B. Okay, so you should have gotten a 7% decay rate for the second one. Here's a couple things that I would like to point out to you about this. So first thing, when I am growing, when I have exponential growth, I take 100% of what I have and I add on to it, right? And so that's really what this 1.09 is saying, is I'm taking a whole part of it, 100% of it, and then I am adding an additional 0.9 onto that. So you can do the math like this. You can do the 1 plus r equals 1.09, or you can just remember that I am having 100% of whatever it is that I have, and I am adding on to it. So I could look at that b-value of 1.09 and tell you right away that it's a 9% growth, because I know that I have an additional 0.09 on my, in addition to my 1, right? Similarly with decay, decay is getting smaller, right? So we are getting less than 100% of our value. So if I look at that 0.93, I can think about, well, how much would it take me to get up to 100? Well, if I'm at 93%, to get up to 100%, I need to add on 7. So that is a 7% decay. Just kind of another way that we can think about that. Okay, fun stuff. I love compound interest. So this is what's next. When we are doing a compound interest problem, here is what I like to do. I like to pull out the information that I have first and then plug stuff into my equations afterwards. And I label things as I go. So you deposit $300 in a savings account. Right away, I am noticing I have this $300 right here. And that seems important. That's not what I wanted. Okay, I have $300. That $300 is what I am putting into the bank. So that $300 is my principal. I deposit $300 in a savings account that earns 3% annual interest. This also seems important, 3% annual interest. This means that my rate of change, 3% as a decimal, is 0.03. And here's where we're going to look at this compound, how many times it's compounded per year. So this also tells me that it is compounded monthly. That means over the course of 1 year, I'm going to compound this amount 12 times because I'm doing it every month. And I might write just n equals 12 here so that you know that. Okay, this is where it gets pretty simple, right? All we're going to do is plug these numbers into our formula. So we have y equals P, my principal, is 300 times 1 plus my rate of 0.03 divided by n, which is 12. All of this raised to the n times t. And that's it, right? I could simplify this, and I'm going to. I have 300. I need to figure out what 0.03 divided by 12 is. And it's going to give me 0.0025. So I would have 1.0025. All of that raised to the 12t, I almost messed up here, 12t power. Okay, couple things that I have seen that are trouble spots for people. First thing is to remember to divide by 12. I have had lots of people that have just done the 1.03. That is not going to work. You will not get the right answer for that. The other thing is to remember this 12t up here. Those values matter a lot. Your answer will change based off of what you plug in there. So those are really important pieces that you need to remember to put in. Okay, so let's do something with it. On your own, I would like you to calculate what the balance would be after 5 years. So I'll write our equation up here. Y equals 300 times 1.0025 raised to the 12t. So what I want to know is what happens when t equals 5. Okay, so go ahead and solve this one on your own and then check your answer back here with me. Okay, so what you should have gotten is $348.49. I've had people ask me, well, Ms. Olson, how do you know what to round to? Well, we're talking about money, right? So if we're talking about money, what do I need to round to? I know that my cents is 2 decimal places after, right? So when I'm talking about money, that's how I know where I'm going to round to. If you did not do this in the right order, you would not have gotten that. So if you did not get what I got, make sure you check back your math to see where it is that you might have gotten wrong. Okay, example 5. So now we're kind of shifting gears a little bit. We're going back to exponential growth and decay. So the table shows the balance of money in a market account over time. So I'm going to take account of what I know. First of all, I'm noticing that these values are increasing. So I know that this is going to be exponential growth. So right away I'm going to make sure that I have that equation for exponential growth. 1 plus r to the t. Okay, my a value is what I'm starting with, or my principal. So I can see right away I'm starting with $300. At year 0, I have $300. Okay, and if I look at what happens the next year, so after 1 year, I have gone up to $312, right? So when t equals 1, my y value is 312. I am going to use that information to be able to solve for my rate. So at 1 year, I have $312. So here's how we're going to set this up. 312, my a value is 300 because that's what I'm starting with, times 1 plus r raised to the first power. So think for a second, why is it that why would I choose year 1 to work with? Well, what is something raised to the first power? Anything raised to the first power is just itself, right? So this exponent here is kind of useless. I don't need it because anything raised to the first power is just what it is. So at this point, I can just solve this like I normally would. So I will distribute this 300. So we'd have 312 equals 300 plus 300r. Subtract 300 from both sides, we get 12 equals 300r. Then we're going to divide both sides by 300. So we've got 12 divided by 300 is 0.04. So my rate, r, equals 0.04. I am not done, however, because what this is asking me to do is write a function. So now I need to use this rate and plug it back into my equation. So I have y equals 300, and then 1 plus r is going to be 1.04 raised to the t. And that's it. Here is the function for our table. Hope that wasn't too bad. Okay, so part B then asks us to graph the functions from part A and our previous example, and then compare the balances. So we're just going to pull up Desmos here. All right, so we'll get this out of the way. Part A was y equals 300.04 raised to the t. And then I have y equals 300.0025 raised to the 12t. Okay, question. Why is it that I do not see any of my functions? I hope that it's obvious to you, but my starting point, my y-intercept, is 300 for both of them. So there's no way that I'm going to see this right now. So I have to change my parameters here. Let's go from 250 to 400. That works. Zoom out a little bit. Here are my two functions. Okay? I can notice, first of all, that they start at the same spot. Right? I'm starting with the same amount of money in both places. So here's what I want you to think about, is which of these two functions is going to be a better investment for you. So I am putting $300 in the bank. It's earning this amount of interest in either place. Which one is going to be a better investment? So I hope that as you're looking at this, you recognize that this red line is steeper, it's increasing faster than the blue line. And so that means that I would have more money in my account using this this 4% annual increase over whatever our compound interest was from before. Something else to think about is that in this specific scenario, I have money in a bank, right? So I am trying to earn interest on money. I'm saving up money. If instead we were talking about money that you owed someone else or of the bank or whatever, the red line would no longer be the better choice, right? Because it's increasing faster, which means that you're going to earn money or you're going to owe money quicker than you would otherwise. So if we were instead talking about money that you owed someone else, we would care more about the blue line than the red line. That would be a better deal for us. So part B, really what we need to notice is that the graph of part A is a better investment because it increases faster. Okay, great. Good. Last example, I'm going to have you do this one on your own. So, you deposit $500 into an account that earns 9% annual interest, compounded monthly. Write a function that represents the balance y in dollars after 3 years. So here, there's two things that I want you to do here. Step number one is write the function. And your formula for that, you're going to use y equals p times 1 plus r over n raised to the n times t. That's the first thing you're going to do. Second thing I would like you to do is find the balance after 3 years. Okay, so go ahead, pause this, do your work, and then you can check your answer back with me when you're finished. Okay, when you are done with this, your equation should have been y equals 500 times 1.0075 raised to the 12t. And then when you plug 3 in, right, we would do 12 times 3, which is 36. You would have taken 1.0075 raised to the 36th power times 100. So we can go ahead and do this in the calculator too. So I would have, first we would do 1.0075 raised to the 36th power. Okay, and then I would take this whole amount and multiply it by 500. And there is our answer. Okay, this is it for 6.2.